Okay, so let's get started today. We got a couple things coming up that need to deal with. Actually, give me 1 second. I got to plug in my smart tablet. There we go. So first of all, a week from tomorrow, so we're talking about Wednesday, April 22nd, is going to be the coding portion of your final exam. So in lab, you'll be doing the coding portion of the final exam. And like last time, it will be 3 problems in Code Assessor, which I'm going to abbreviate as CA. And you'll have the full period in which to do it. I anticipate that in sum total, they will be worth 50 points. And as in the past, you'll be allowed a 1-page cheat sheet. During the regularly scheduled final period, we will be doing the paper-based version. So let me just quickly check that because I have it here on the... That's going to be, well, I don't have it. So we'll just say during the regularly scheduled final exam time. There will be a paper exam. I haven't yet decided how many problems for that, but so paper exam, no coding, just like the previous ones, probably worth 70 points in total. And the topics that we are covering are the topics since the last midterm. So this isn't comprehensive final, it is much like a midterm instead. So linked data structures, lists, stacks, queues, trees, recursion, and what we get through to the end of the semester, which will be also AVL trees, B trees, big O notation will be the topics for the exams. Logically, you can expect that the 3 major topics that we've considered have been lists, recursion, and trees. And therefore, most likely, there will be 1 coding problem covering each of those 3 topics. So, questions about that? Okay, so that's a week from today. Then, there's also 1 final extra credit opportunity involving SIIS. So if you complete it, you can get up to 30 additional lab points. So to do that, you need to submit a signed confirmation sheet. The reason it needs to be signed is because your name's not on it otherwise. We need your name. Okay, so a signed confirmation form and bring that to lab on April 22nd. So I definitely do not want to receive email with it. That just is an enormous headache. So print it out, bring it to lab on Wednesday, April 22nd, and that will be worth 30 extra credit lab points. So SIIS actually closes usually the last day of classes. It doesn't make any sense to delay it until the final because they actually take it down and you can't get the confirmation page after that. Okay, so those are the two announcements, and we are going to today finish up with AVL trees. So we're going to review very quickly what they are and how to do rotations. Then we're going to show you how to do inserts and deletes in them. Turns out that the find operation is identical to the find operation for a binary search tree, because an AVL tree is still at heart just a binary search tree. It's a balanced binary search tree. In fact, pretty much the code that works for printing or returning the size or finding an element is the same, whether for an AVL tree or for a binary search tree. And you'll find that for the final lab, where you're doing an implementation of an AVL tree, pretty much the best thing that you can do to start the lab is to simply copy Dr. Planck's BS tree code, because the AVL tree code essentially just builds on that code. So that's the first thing I did when I did lab 11, which is the last lab. I just copied his file in total, and then I just modified it. Okay, so remember, the goal behind an AVL tree was to keep our binary search trees relatively balanced under any insertion order. So the goal is to keep a binary search tree, which I'm going to abbreviate as BST, balanced under any order of insertions. Okay, and we showed you an example last time where if you inserted data in sorted order, it led to a long linear chain for a tree rather than a balanced tree, and that led to the worst case order n times. So what we're going for here is a guaranteed order log n time for our insert, delete, and find, because if we have a relatively balanced tree, then all of these operations should take order log n time. And the reason is, with a relatively balanced tree, every subtree is going to contain roughly half the nodes that are in the tree. So our balance condition for an AVL tree, does anyone remember what that balance condition is?
The left minus the right is greater than or equal to 1.
So less than or equal to 1. We want them to be within 1, the height should be within 1 of each other. So if it's greater than 1, it's unbalanced. Okay, so the balance condition is that for every node in the tree, the height of the left and right subtrees differ by no more than 1. And it can be proven, we won't do it, but it can be proven that if this balance condition is maintained, then it's close enough to each subtree having half the remaining nodes that our log n performance is indeed guaranteed. So what that means is that when we do an insert or delete, that is, when we remove or delete a node from the tree, it's quite possible that the balance condition is going to be violated. So a very simple example, let's say we insert 0, 1, and 2 into a tree. So when we insert 0, it just becomes the root. When we insert 1, it's placed to the right of 0. And this is still an AVL tree because if we look at the height of 1 is 0, and the height of 0 is now 1. The height of 0's left subtree, which is non-existent, is by definition -1. So we see that the difference in height between any two subtrees is no greater than 1. So this is in fact a legitimate AVL tree. But now when we insert 2 and we look at our balance condition, the height of 2 is 0, the height of 1 is 1, and the height of 0 is now 2. If we look at, first of all, the heights of 1's two subtrees, that's fine. They differ by no more than 1. But if we look at the heights of 0's two subtrees, we find that they differ by more than 1. And therefore, something needs to be done to rebalance this tree in order to convert it back to an AVL tree. And the way that we do that is using something called a rotation. Okay, so in this case, the rotation is going to be about 1, and we'll show you shortly how we identify the node about which we perform the rotation. But in this case, it's called a rotation because we swing 0 down so that 0 becomes the left child of 1. And when we do that, we obtain a AVL tree, because if we look at the heights of our two children, they're both 0. They differ by no more than 1. So we have a valid AVL tree. So this rotation is going to be the critical operation that we use to rebalance our trees. And we'll see that we also use these rotations when we delete an element from a tree. So we did cover rotations last time. And you'll remember that what happens is, in this case, with B and D, we're rotating about D. It's called a left rotation about D. So what happens is B comes down and becomes the left child of D. That's what you see over here, that B has become the left child of D. You can see that this subtree C, something has to be done with it, because when B becomes the left child of D, C becomes an orphan. It's as though it no longer has a parent. So something has to be done with it. Well, conveniently, when we make B a left subtree of D, B no longer has a right child, because D used to be its right child. It no longer is, so B is free to adopt C as its right child. Okay, and we showed that this is a fine rotation that maintains all the proper inequalities in the tree. So we knew that over here everything in A had to be less than B, because A was the left subtree of B. And everything we knew that B is less than D, and that everything in C is greater than B, because C is in the right subtree of B and in the left subtree of D, so everything in C is between B and D, and then everything in E is greater than D. So that was true on the left side. On the right side, we have that for sure B is less than D. That's what this relationship is all about. Okay, this relationship here says that we still have everything in E is greater than D. Okay, this relationship here between B and A, we still have A is less than B. And finally, we put B or C as B's right child, and in fact, we know that from this inequality right here, in fact, we put a C in here, that is quite true. And that's what this relationship is saying. C is in B's right, or C is B's right subtree, so everything in C must be greater than B, that's true. And C is now in D's left subtree. C, in fact, is less than D. So the rotation has maintained all the proper relationships. So we still have a valid balanced, or not balanced, but a valid binary tree, search tree, when we're done. Okay? And we could do the opposite. We could go this way, in which case we would be doing a right rotation about B. So that's why right here the notes say rotation about B. So that's going to be the key idea behind our rebalancing. Okay, and there was a question on Piazza yesterday about, well, being a little confused about how to proceed with actually programming this kind of rotation. So if I have my procedure rotate and I receive a node N and I want to rotate about it, okay, the first thing I need to do is I need to identify the parent. So if N is equal to D, the first thing I need to do is I need to identify the parent. Well, how can I identify the parent?
Look at the parent node in B.
Very good, which is we have a parent pointer. So we can very easily get a hold of the parent pointer by just saying parent equals N parent. Okay, that's why one of the reasons we keep track of our parent. So now we know who our parent is. Now we need to decide whether we're performing a left rotation or a right rotation. Okay? Well, how would you make that determination? How do you know if, in this case, how would you know that D is the right child of B? How would we know that? Yes,
Greater than or less than.
Greater than or less than? Yep. So one way we could do is we could simply do a check and say if parent key greater than or equal, well, in this case we are guaranteed that there's no duplicates, so that's one way to do it. And the other way is just to check. We know that, so the other way is to simply say if parent, say left equal N, then it is this case right here, and we're doing a right rotation. Okay, and this is where you need to get used to it. There's no reason to put a second else. If it's not a right rotation, it must be a left rotation. Okay, so if it's a left child, we perform a right rotation about it. If, as in the case of D, it's a right child, we perform a left rotation. Okay? So now, exploding, let's do the left rotation because that's what we've been so far focusing on. So bring that down here. So if we're going to do a left rotation, that's what we're doing right here, a very important thing is to get a hold of the subtree, which is C. We need a pointer to that subtree because it's going to move around. Okay, so we can, in this case, say C subtree equals N of left, because it's the left subtree. And now it's just a simple matter of changing pointers. We have now a pointer. We have all of our pointers that we need. We now have N pointing to D. We have parent pointing to B. And we have a pointer called C subtree pointing to C. So now it's simply a matter of looking at this diagram over here and saying, okay, B becomes the right child of D, so it must be that N's left is equal to the parent, because the parent points to B. So now we've taken care of this new relationship. Okay, another new relationship is that B's right is equal to C, so we need to say that parent, which is B, its right is now equal to C subtree. Okay, if we look, none of the other left or right pointers seemingly have to be adjusted, right? Because the pointer B's left still points to A, D's right still points to E. But there's something invisible here that needs to be adjusted. Not the sentinel, the parent of B. So we actually have one more thing. So we don't know whether B is a left or right child, so I'm just going to assume that B is a left child, but there's no reason for it necessarily to be the left child. It could be the right child. But the point is that B has become a left child of D, and D is replacing B. So we also are going to have to make B's parent, it needs to point to D rather than to B. Okay? So there's another operation here that we have to perform. And I'm going to have to get myself room, going to have to erase. So if everyone got this down. Okay, so I'm going to have to erase it. Actually, do it like this. Okay, so I'm just going to, in this case, to make it clear, say B parent equals parent parent. I know that looks funny, but that's the way you get B's parent, because parent is a pointer to B right now. So again, you need to check to see whether B is a left or right child. So if it's a left child, then we make B parent's left be equal to N, else we make B parent right equal N. So we're just replacing B with D right there. Okay, and finally, I'm not going to show it because I think you should be able to figure out how to do it, but you need to adjust all the parent pointers. Okay, so B's parent changed, D's parent changed, C's parent changed, so you need to adjust all the relevant parent pointers. So that handles the case for a left rotation, and I'm going to leave it to you to figure out how to do the mirror case, which is the right rotation. But that gives you some good pseudocode for doing the rotation. So questions about that? Yes, Scott.
I don't have a question about this actually, but
Mm-hmm.
I was doing something in this function. So it gives us the key for the node that
Mm-hmm.
we need to rotate about. Can we use the find function to
Yes.
find it? 'Cause
Yes.
the find returns a void star, and I don't know how to use that.
So, okay, so the question, actually you cannot use the find function
Okay.
because of that. It doesn't return a node.
All right.
So the question was, if you look at the, just a sec, before I answer that question, any other questions about this? We're good?
So
Doug.
the parent is the parent of the thing you're bringing down.
It is, yes, it is the parent of the thing that is being rotated about in this case. So B is the thing that is being rotated down. So it's the parent of whatever is getting rotated down. Other questions? Okay. So Scott's question had to deal with, if we look at the, in fact, we can look at, no we can't. Let's look at, for the B trees, so you have to go and look at the labs. Nope, have to look at the notes. So you're having to find the node that you do. So there's still not. I need two things. Okay. Let me leave that up. And then let's bring up the lab as well. Okay. So with rotate, you get a string, not a node. So the first thing rotate has to do is find the node associated with that key. And Scott's question is, could I use find, could I call the find function to return that node? And the answer is, we got to look to see what find returns. Find returns a void star, and that void star is a pointer to the value. That's no good. We want a pointer to the node. So you're not going to be able to use the find function. Instead, you're going to have to write your own mini code to find the node and then proceed from there. Okay. Okay, so let's move on and actually look at, well, let's get back to the AVL. So let's look at, we already did some rotation, so we're not going to do that. So let's look at how we use a rotation to rebalance an AVL tree. Okay, so when we insert into a tree and there's an imbalance, there's essentially four cases. So what I'm going to do is when we insert, and we find an imbalance. Let's say we're at this node when we find the imbalance. So we know that there's a difference if the height of, let's say this is, say, h, then we know that one of these must be h minus 1, and one of these, I'm sorry, that is not true. We know that one of them is going to be second, get this right. This is h minus 1. Yes. This is h minus 3. So we know for a fact that if this is h, then in order to get h, one of the two subtrees must be h minus 1. Okay? Guaranteed. That means the other one must be h minus 3, a difference of 2. Not going to get into it, but there can't be a height difference greater than 2. That's guaranteed. If we're moving up the tree and we previously had an AVL tree and we do an insert, there is no way that the balance condition can be off by more than 2. So if we have an imbalance, it's either this way or it's going to be the other way where it is h minus 1 here and it is h minus 3 here. Okay, so it's going to be one or the other. Okay, so that starts with the first two cases. So let's get rid of this for a moment and focus on this case. So in this case, the problem is that this subtree is sticking down further than this one. So if we were to count levels, let's make it even more obvious. Okay, there's a difference in height of 2 here. So the first thing we need to do is figure out whether the insert into this subtree right here, whether that insert was into the left part or the right part of it. Okay, so there's two cases. Okay, the insert could have been somewhere, in the left subtree, or it could have been somewhere in the right subtree. Okay, if it was the insert occurred in the left subtree, it sets up what we call a zigzag situation. And if it was into the right subtree, it sets up what we call a zig-zig situation. Okay? The so-called zigzag because we first went right and then we went left. And zig-zig because in both cases we went in the same direction. Okay? So if you think back to my example at the start of class, where I inserted 2, okay? So the imbalance occurred right here, and the insert was right here, so it's a zig-zig situation. Okay? If instead I had had a tree where it was, say, 5, 8, and now the insertion was 6, this would have set up a zigzag situation. Okay, because here's my node where the imbalance is. The bigger or higher tree is over here in the right subtree, and then the insertion occurred in its left subtree, creating a zigzag situation. Okay? And we have a so-called mirror situation if instead we had the left tree being bigger and the right tree being smaller. Okay, again, the insertion could have either occurred in the left or the right subtree. If it comes down the left side, it's a zigzag. And again, if it comes down the right side, it's a zigzag. Okay, so we kind of talk about the zig-zig situation as being an insertion into the outside of the so-called outside of the tree. The outside of the tree. And a zigzag as being an insertion into the inside of the tree. It's going to turn out that the Zig Zig insertion is easier to handle. Okay? So, if we have a Zig Zig insertion, okay, and I'm just going to arbitrarily choose the left side as having had it. So this is our situation. The red node is the imbalance. Okay, this is H minus 1, this is H minus 3, and we're going to assume that the insert was into this left subtree. Okay? So our situation, based on what you saw earlier, is here's B, here's D. Okay? And we are going to be doing a rotation about D in order to fix it. So the way we fix a zig-zig situation is we rotate about the child of the imbalanced node. Okay, so in this case we're going to rotate about D. Okay, so let's see what happens in this case. So in this case, let's draw the other tree. Okay, we're going to say that the height here is, let's see, it was, say, 3 here, then it would be 2 here, and 0 here. So, going to make this height be 1. Yes, we'll make this height be 0. Okay. So that is right. So I often find it easy to also resort to concrete situations. So this would be H minus 3, and this would be H minus 2. And what we're going to do is we are going to be moving B down. Okay? When we move B down, we're moving this tree right here down 1 level. Okay? So if we think of, let's try to get my balance, my things all balanced out here perfectly. Okay, so this is here we are, and actually let's do it with a real tree. It'll make it a lot easier to understand if I do it with a real tree. Show you what's going on. So let's do a real tree. We'll make this 16. We'll make this be 5. We'll make this be 3. And we'll make this be 2. We'll make this be 8. So the insertion of the 2 is what messed us up. Okay, so if we look at the heights here, height here is 0, 0, 1, 0, 2, and 3. But the imbalance, the first place I have an imbalance is right here at 10. It's the first time that any child differs by more than 2. Therefore, we're going to be rotating about its child 5. Okay. Yes, Doug?
I thought it was that they differ by more than 1.
Yes. So the first place they differ by more than 1 is right here. Okay, that's the first place they differ by more than 1. So we're going to rotate 10 about 5. So what's going to happen is 16 is essentially going to move down a level. So if we look at what happens, 5 in some sense moves up, and 10 and 16 get forced down, and we have that 8 gets adopted by 10, and 3 and 2 stay in the same place. So what happened was, it's hard to show, this is one thing where it helps to have some dynamicism, but this 10 swung down, and in swinging down, 16 dropped down a level. It dropped down to the same level as 8. Okay? And this 2 got shoved up. This 2 got brought up a level. Okay? Because it got dragged along with 5. 5 got promoted up. So 2, 3, and 5 got dragged up. Okay? And as a result, if we look at things now, 0, 0, let's do it with blue, 0, 0, 0, this is 1, this is 1, this is 2. You see nothing is off by more than 1 anymore. So basically what happened is with this rotation, the right side gained 1 in some sense. It didn't really gain 1 in height, but the right side was pushed down. So I'll say it that way. Right side was pushed down 1 level. And the left side was pulled up. And that serves to rebalance the tree. And again, it can be shown, we're not going to do it, but it can be shown that once you've done this, that the height of this new node, which is 5, is the same height as it was in the old tree before the insertion. That is, before we inserted 2 into this tree, it was in fact the case that 10 had a height of 2. And after we do the insert and rotate, 5, which assumes 10's position, also will have a height of 2. Okay, so after the insert, or after the rebalance, so after the insert and rebalance, the tree rooted at the node we rotated about has the same height as the original tree before the insert. And therefore, you don't have to go any further. There's no further rebalancing required because you knew in the original tree that it was a legitimate AVL tree. Therefore, if the tree rooted, in this case at 5, has the same height as 10 originally had, we need look no further up the tree. Okay, so it turns out that a single rebalance is all that is required in this case. Okay? So this is the zigzag, and it works exactly the same way if the insert had occurred on the right-hand side. It's just a mirror situation. Okay? The zigzag turns out to be more complicated. Okay, so let's look at a concrete example of a zigzag. So let's do 8, 5, and 6. So that's a zigzag situation. Okay, if we look at the heights, 0, 1, 2, minus 1, we see that 8 is not a legitimate AVL tree. And we have what's called a zigzag situation. So let's try and fix things by doing our rotation about 5. It worked so well last time, let's do it again. Okay, see if it works. So if we do a rotation about 5, first of all, see if you can do it yourself. Okay, you're doing a rotation about 5. See if you could do it yourself. Figure out what the tree. Take about a minute. Figure out what the tree should look like. If you rotate.
Can 5 be on that side?
Oh, thank you. I see why everyone's looking at me like I'm from the moon. Okay. What did I want? I want them swapped. Thank you, Gerald. 5 and 8. Okay, now do it. So we're now actually doing the rotation about 8. So what happens is 5 slides down to become the left child of 8. And now 6 becomes an orphan. Okay, so when 5 slides down, we'll send 6 out to the sidelines. And 5 becomes the left child, which means that 5 adopts 6 as its right child. So we've gone from this situation where we had 5, 8, 6, to the situation we have on the right if we do a rotation about 8. Has that helped us? Is this an AVL tree on the right? It is not. Okay, if we look, 0, 1, 2, minus 1, we still have an imbalance about 8. So it didn't do us any good. The fix that worked in the zigzag case doesn't work in the zigzag case. Turns out that in the zigzag case, what we're going to have to do is what's called a double rotation about 6. Okay, so what's going to happen is we're first going to do a rotation about 6, and if we do that, the 8 comes down, swivels down to become the right child of 8. And now it's a double rotation, so we're going to again rotate about 6, meaning that the 5 swivels down, becoming the left child. And that rebalances the tree. So if we have a zigzag situation, then we perform a double rotation about the grandchild okay, and the grandchild roots the tree where the insertion occurred. About the grandchild that roots the subtree where the insertion occurred. Okay, and it's a very simple code. If you look at what the rebalance looks like, if n is a pointer to that grandchild, it's just 2 calls to rotate. Actually, let me make it be clear that it's the grandchild. So it's simply 2 calls to rotate. And that does the trick. So that's why we call it a double rotation, because you rotate about the grandchild, and then you rotate again, and it ends up being at the root. Not of the root of the entire tree, but being at the root of the imbalanced tree. So what happens, okay, if we have this situation, so we have n, and here we have p for parent, and here we have, say, g for grandchild. Let me go to another page, because this is getting too small. So our situation is we have our n. This is where the imbalance occurs. Then we'll say P, and here's G for grandchild. So this is a zigzag situation. And let's now set up some other trees. Here's A, here's B, here's C and D. Boy, I should have said, I'm going to do the same thing, but there's no reason to put this in the middle of the screen when I'm going to need the whole screen. So N, P, G, A, B, C, and D. So the first rotate is going to bring P down. P is going to swing down. So if we look at it, start with G, the P swings down, holding on to its B. And what does P inherit as its left child? D. Very good. And G hangs on to its child C. So now we have this situation. N still has its child A, so that's rotation 1. Rotation 2, now rotates N down. Okay, N holds on to A. And what does N inherit as its right child? C. Very good. And here's P, D, and B. And voila, it's a lot more balanced when we're done. Okay, so you can see what happens is if you look at this path, in the end, P became the right child and N became the left child. And G got pushed up 2 levels. Okay, yes, Ardalyn. Very good. Yep. So in a zigzag situation, there's 1 rotation about the child. In a zigzag situation, there's 2 rotations about the grandchild. Okay. So once you've written rotate, it's actually quite easy. You just identify which of the 2 situations exists, and you either call it once or you call it twice. Okay. So the code's actually not very hard to write. It's more a matter of bookkeeping. Okay, and the situation here is the same as we had before. So after this double rotation, the height of the tree is the same as before. So after this double rotation, the subtree rooted at G has the same height as the original subtree rooted at N before the insert occurred. Okay, and therefore, again, we don't have to do anything else because we know in the original tree that above N, the tree satisfied the AVL condition. Since after our double rotation, the subtree rooted at G has the same height, by definition, we still must have a AVL tree above us. All the nodes up to the root still obey the AVL condition, and therefore we're done. Okay? So that's an insert. We just do either 1 rotation or 2 rotations depending on where we were. Any questions about that? Well, we got some practice for you. So, if you go to my notes, you will see AVL rebalancing tree, and if you can't do it, then here it is. So what I want you to do is take a moment and first try to rebalance the top tray. So the insert is 12. You should be able to figure out that it's 12 from the fact that that's where the tree seems to be too big, but that's where the insert occurred. So first of all, just before you start, figure out where the imbalance is. First, take a moment and let's discuss where the imbalance is first. So we make sure when we rebalance, we're doing it from the right place. Okay, we're going to take a poll. How many people think that, so the imbalance, if it occurs, has to occur on one of the nodes going to the root. So it's going to be one of these three nodes. So how many people think that the imbalance occurs at 16? No one. How many think that it occurs at 10? Okay, a couple people. And how many think it occurs at 20? Okay, the majority of you. Well, let's see. Start here at 0. This is 0. This is 1. This is 2. This is 0. This is 3. So if we look at 16, that's fine. It's two children differ by no more than 1. If we look at 10, its two children differ by no more than 1. If we look at 20, its two children do differ by 2. So in fact, the first node about which is unbalanced is 20. Therefore, we need to do our rebalancing somehow with 20. Okay, so rebalance this tree knowing that the imbalance is at 20. Okay, so going to go over the solution. So if we look at where the insertion occurred, the insertion was 12, so it's occurred in the left subtree for 20, and it occurred in the right subtree for 10. So this is a zigzag situation. And we're going to have to do our double rotation about 16. Okay, so what that means is we're first going to swing 10 down. So 10 is going to become a left child of 16, and it will hold on to its left child, which is 8, and it will adopt 12 as its right child. So after the first step, it looks like this, and you can see we still do not have an AVL tree. So to fix that situation, we do a second rotation about 16, and now 20 swings down. So 20 comes down, holding on to 40. And 16 has no right child here, so 20 does not have to adopt anything. 16 holds on to its left child, giving us that. Now this, you may think that this doesn't look super balanced, but if you do the calculations with height, you find out that indeed, if you look at any node in the tree, there's never any more than, in fact, there is no difference in the heights between any of the subtrees. So in fact, when we're done, it's a valid AVL tree. Okay. Now, I'm not going to go over 2. I'm going to post the solution, but I am going to ask the question, if I insert 9 here, the imbalance again occurs at 20. I'll just tell you that. And the question is it a zig-zig rotation, or is it, I'm sorry, is it a zig-zig situation, or is it a zigzag situation?
Zigzag.
So let's take a vote. How many think it's a zigzag situation? Okay. Don't be shy. Could well be. And how many think it's a zig-zig situation? Okay, it's about 50-50. It's actually a zig-zig situation. Okay, this is where you're thinking, well, wait a minute. It looks like it's an inside insertion. But that's not what you're looking at. The imbalance actually occurred at 20, so you have to look at, did the insertion occur in the left or right subtray? Well, 9 was inserted into the left subtray. So now we're looking at 10, and the question is, was the insertion into the left or right subtree of 10? It was into 10's left subtree, and therefore it's a zig-zig situation. So you don't ultimately go all the way down to 9 in this situation. You look at the node that's imbalanced, and you look down 2 levels. And the question is, when you look down 2 levels, is it zig-zig or zigzag? If you look down 2 levels, it's zig-zig. Okay? So questions about that?
Just go over that one more time.
Yes. So when you are determining whether it's a zig-zig or zigzag, you start at the node where the imbalance is detected. You look down 2 levels. Okay? So first level, here, the insert occurred in the left subtree. So that's looking down the first level. Okay? Now, you're at 10, and you need to know whether the insert occurred in its left subtree or its right subtree. And again, the insertion was in its left subtray, and therefore it's a zig-zig situation. Even though if you just eyeball it, it's going to look like it's a zigzag, but it's really not. Okay. Other questions? Okay. I'm going to just quickly hit delete, and then I'll hit it again on Thursday. So delete, and I will post the solution to figure 2. So I'll have that solution up later today. So deletion is just taking the operations that we have been considering so far and putting them together in the right order. So we delete initially just like we delete it from a binary search tree. We have 3 cases. Okay, so case 1, we'd be deleting a mod here, which is a child, or here Callista. So case 1, we delete a leaf. Case 2, we would delete a node like baby Daisy where it has a single child, in which case we would replace baby Daisy with its single child. And the last case is where we have a node with two children, in which case we find the largest key in the left subtree, delete that key, and then replace Binky with that key. So in this case, Binky would get replaced with baby Daisy. So the first step of the delete is identical to the delete with a binary search tree. That's why I said just copy Dr. Planck's code and modify it. After you've performed the delete, you need to check to see the rebalance condition. And it's really very simple, okay? All you do is you start by checking the parent of the deleted node. And you just chase upwards, so basically delete, okay, step one, delete just as you would in a binary search tree. Okay, step two is to now check to see whether we still have an AVL tree. So starting at the deleted nodes parent, check the balance condition and rebalance if necessary. And this is just like with an insert where you'll find out whether the imbalance is on your left or your right, and you will, based on that, figure out whether you have a zig-zag situation or a zigzag, and you will perform the necessary thing. Unlike the insert situation, we will find that multiple rebalancing operations may be necessary. So 3 is repeat the traversal to the root, rebalancing each parent that requires it. So we will see on Thursday that it is not always the case that one rebalance operation takes care of it. In fact, we may have to do it more than once. Also, just warming up for Thursday, you'll see that the imbalance can occur on the, quote, opposite side of the tree from where the delete occurred. So in the insert, it was always the case, let's say we insert it here, aardvark, then the imbalance must occur on the side of the tree where the insertion occurred. That's where the imbalance is. But with the delete, it is more than likely, if we delete Callista, where is the imbalance now coming from? We deleted Callista. The imbalance, is it on Callista's side of the tree? No, it's on the other side of the tree because a delete tends to shorten the side of the tree on which the deletion occurred, right? Therefore, the imbalance, when it occurs, is going to be on the other side of the tree. Does that make sense? So now, when we do our search to see whether we have a zigzag or a zigzag, it's almost certainly going to be the case that when we look for the imbalance the imbalance is going to be on the opposite side. So we'll go over this on Thursday. Don't worry, you will not get to delete tomorrow in lab, I guarantee it. You'll have your hands full just getting rotate and inserts to work. So we will finish up with deletion on Thursday, and then we'll move on into B trees on Thursday.